Okay, so this lecture is meant to introduce you to the safety mechanisms that are in place when you have any type of electronic circuit. And so first, let's look at the why we need to have these safety mechanisms. So naturally, when a current flows through a wire, the wire is going to heat up due to molecular collisions. And if you have them colliding enough, there's going to be too much friction, and that's when your wire is going to get hot. And if your wire can get too hot, then it's going to physically melt your wire, and there won't necessarily be that connection, and that live wire can cause definitely problems. So there are three basic mechanisms that are meant to minimize the amount or minimize the reality of having something in your system burn up. Okay? So instead of maybe transferring, when it melts, transferring that energy to a component in your circuit, it basically cuts the circuit. So the first two mechanisms deal with just cutting the circuit, opening the circuit, preventing it from flowing anymore. And the first one is a fuse. And a fuse is essentially a small encapsulated wire that is designed to melt when too much current goes through it. So this is essentially something that's designed to break open the circuit. You can have different size, different rating fuses. Clearly, the thinner the fuse is, the smaller amperage it can go through it before it's going to melt it. You can have really thick fuses, and when you come back into class, I'll show you the differences in thicknesses in the wire that it has to actually melt through. The nice thing about fuses is that they're easy to replace. The bummer is that you've got to replace them. So in applications where you're not as likely to have too high of a current, you're going to use a fuse, and it's just that added safety mechanism. When we get back into class, well, when we get back to class, I'm going to talk to you about how this relates to plugs of different sizes. But I want to have you live with me before I do that. And when I say plugs of different sizes, I'm talking about how you have a standard plug, and one of these is a little bit bigger than the other. It's that annoying thing, like when you go to plug it in, you're going to have to turn around and plug it in. We'll talk about why things that have this type of plug are things that have fuses in them. Okay? So the second type of safety mechanism, again, is designed to open up the circuit, and it's called a circuit breaker. And a circuit breaker is essentially a bimetallic piece of metal, a bimetallic strip of metal that is embedded in the circuit. And when too much current goes through the system, the bimetallic strip heats up and it bends. And in bending, when it bends, it creates a gap in the circuit. Okay. So essentially, let's hope that this purpose doesn't need this before. So if you were to kind of think about a circuit breaker, usually you have a in your house you have the terrible roof. You have like a circuit breaker box, and I'm going to zoom in to the circuit breaker box. Okay. So in that circuit breaker box, you have the incoming wire, and then you have this bimetallic strip, which is two pieces of metal. Again, this is not to scale. So there's one kind of metal and another kind of metal. And then it goes to the rest of your circuit. So let me add a little bit of color. So this is one kind of metal. This is another kind of metal. Oh, this marker is terrible. This is another kind of metal. This one's bad too. Whew. Okay, third time's a charm. Okay, hopefully blue and green show up well in the video. So what happens is when too much current goes through, this thing heats up, and when it heats up, it becomes like this. It physically bends open. So, say bless you to Miss Hartford. Oh gosh. Okay. So it physically bends open, and now there is no ability for the current to run through my circuit anymore. When you don't have current running through it, it's going to cool down, and when it cools back down, it straightens back up, but you have to manually push it back in place. And so some of you may experience a circuit breaker, maybe not necessarily like on the side of your house, but nowadays in most modern homes, whenever you have an outlet that is near water, so in your bathroom or in the kitchen, they have these, they're called ground fault interrupt outlets, but essentially they have a little red button, black button, and sometimes just white. But if you trip that circuit breaker, you have to push the button back in place. So you're physically just pushing it back in place and locking it, okay? So that's an example of a circuit breaker. Another example of a circuit breaker is just when you have like a power strip. Some of those power strips have a circuit breaker built into them, not necessarily just like I've got an on-off switch, but there's a side button where there's a circuit breaker. And next week when we talk about the idea of having multiple resistors in a given circuit, we'll talk about what the benefits are of having that in a circuit breaker, in a power strip. Okay? So that's a circuit breaker. And then the third one isn't necessarily meant to open up the circuit if there's too much current, but it's just this added safety mechanism for things that draw quite a bit of current. So the third one is a grounding prong, and I'm going to call it AKA the third prong. So when you have something that uses electricity, it always has the two, usually they're like rectangular prongs, and that's standard because we have to have a voltage difference. If they're going to have a fuse, one of those is going to be a little bit larger. And if it's something that draws quite a bit of current, it has that third cylindrical prong. And so this is an added 0-volt line. That grounds the device. In case of a mishap. So let's kind of talk about what a mishap is. So again, this is not going to be the best picture, but it'll be fine. This is not to scale. So you've got your, this is my plug, right? And so it goes to plug in my awesome microwave that I just got. Okay, so in any standard outlet or plug, you have one line that is the 120 volt line. You have the second line that is the 0-volt line. And that essentially is what causes your device to function, right? You have a voltage difference, all these components work, etc. And then when you have this third one, it's another 0-volt line. That doesn't actually even go to the electrical components. Like, it has nothing to do with the electrical components. You could, I wouldn't recommend it, but you could physically like cut off that one and your device is still going to work just fine because it has nothing to do with the functionality here. It has to do with the fact that, let's say that there is some kind of a mishap in the wiring. You nudge this, you bump this, something happens, and all of a sudden your 120-volt line touches some metal piece of the microwave. Without you even knowing it now, the whole microwave, which happens to be metal and happens to draw quite a bit of current, is now 120 volts. So you can go and touch it, and then you are going to get electrocuted. It's like you just touching a 120-volt line with a lot of electrons, access to a lot of electrons. So what this 0-volt line does is anytime it has this happen, where the external casing of your device is touching the live wire, it immediately grounds it so that you do not get shocked. So you're only going to see this third prong in a device that tends to draw a high current. So if you have something that's drawing a high current, then that high current can easily go into you. Okay? So you'll notice not a whole lot of things use that one. So when we get back into class, I'll just do some demos with both a fuse, with the circuit breaker, and go over any questions in this as well.